The spark plug electric field simulation. In this example, we will simulate electric field around the spark plug electrodes. The model includes the ground electrode, high voltage electrode, and the insulator. The electric potential of all electrodes are known, and the electric permittivity of the insulator is also a known value. If you download the simulation files and unpack them, you will find the CAD model inside. It is not needed to perform a simulation, it's just to demonstrate how the model was created originally in the CAD system. You can see there are 3 bodies. This is the ground electrode, this is the high voltage electrode, and this is the insulator. I will export all these bodies to the step file. Spark plug. Okay. Now I will start QuickField. In QuickField I will create new problem. Okay, it will be located here. The problem file name is the spark plug. Spark plug, and this is the location folder. Next I will specify the problem type. It will be the electrostatics analysis. And the model class is 3-dimensional import. Now press finish, and here you can see the geometry model editor window. The only action you can do here is to import the step file. So I press the import button, choose the file, and here you can see the geometry model in QuickField. There are 3 bodies, and the model doesn't include the air. So I will click here to enable the background region. Now you can see the box. The simulation workflow is the same as in 2-dimensional analysis. First, we should assign labels to geometric objects. Block labels are used to define material properties, and surfaces are used to define boundary conditions. To assign label to object, you should select this object. To select the object, you should click it. So I click here, and the surface is selected. To select the body behind this surface, I should click the surface again. So I click it again. Now the body is selected, and I can type in the label name here, air. Next, I would like to assign labels to other bodies, but they are hidden inside the air blocks. How do we know what is hidden inside this box? There are several options. We can hide the box, or we can make it transparent. Right-click the selected body to browse the options. You can hide it, you can make it transparent. Now we can see what is inside the box. But if you try to click the object inside, you will still select the box. The bounding box is transparent, but it covers all the bodies inside. Let's hide the box. Again, first click to select the surface. Next, click to select the box. Right click it and choose hide. Now we can manipulate with other objects. Again, click to select the face, second click to select the body behind this face. That would be the body of the spark plug. Body grounded. OK. Again, I will hide this body to proceed with internal construction. First click to select the surface, second click to select the body behind the surface. This would be the insulator. OK. I will hide the insulator, and this will be the high voltage electrode. I can select it by clicking it, or I can select it using the rubber band. Right click, hold and drag. Now release the button. All the objects inside the rectangle selected. You can see there is one body selected, 5 faces, 7 edges and 4 vertices selected. Right now I will need to assign the label to the body. So I type here the high voltage conductor. Okay, now I will unhide all bodies. Right click and choose unhide all. You see the air block is still transparent. And now I will provide physical properties to the materials. Double click the label in the tree and specify the relative electric permittivity. For the air I type in 1. OK. For the insulator, the relative electric permittivity is 5. And inside the conductors, the electric field stress is 0. We can simulate this by specifying a very high value of electric permittivity, for example 10,000. And the same for the high voltage conductor. OK. Next, I would like to assign conductors' potentials. Let's start with the high voltage conductor. I will right click the conductor label in the tree and choose hide all by this. Now I will select with the rectangle, right click, hold and drag, then release. Now let's check what we have in selection. There is one body selected, some faces, vertices. This time I will assign label to faces. High voltage. And I will double click in the tree and type in the potential value, 10,000 volts. OK. And let's repeat this for the grounded part. I will unhide all, choose the grounded electrode. In the context menu I will select hide all but this. Now with the rectangle I will select everything inside the rectangle, the body and its faces, and for the faces I will type in the label grounded. And for the grounded label I specify 0 electric potential. Now everything is ready. I will again show all objects. Let's verify the model. We have the body grounded conductor, and on the grounded conductor surface we have the zero electric potential. We have the high voltage conductor there in the middle, and on its surface we have the high voltage potential specified. We have the insulator and we have the air block. Now we can proceed with the finite element mesh building. In three-dimensional models, you build the mesh in three stages. First, you build the mesh on the edges, then on the faces, and at last in the volumes. Once the mesh is built, you can run the simulation. Save all files. And here you can see the results. Once again, we can see the box and potential distribution on the box faces. Again, let's hide this box and take a look at the potential distribution at the bodies inside. Okay, we can see the potential distribution. But what I'm interested in is the electric field stress distribution. So I will switch to the electric field strength. And I see zero electric field stress inside conductors, as it should be. But I would like to see the electric field stress distribution in the air. So I need to unhide the air. And again, I see the box. Well, we can use the cut plane to see what is hidden inside this box. We can change the plane direction. And we can see this picture in the separate window. Okay, here we can adjust the field picture independently. I will switch off the field lines. I will switch on the color map of the electric field strength. I can zoom in. I can build the contours here. Left click to start the contour. Left click to add the intermediate point. And right click to finish the contour. So this is the contour, and I would like to see the electric field stress distribution along this contour. So I will switch XY plot. This is electric potential, and this is the electric field stress components. The same you can see in the table. X, Y, Z coordinates, electric potential, electric field stress. And of course you can copy all the data to the Excel tables. You can copy pictures and plots to the Word document. And you can copy color pictures using the print screen button on your keyboard. So I press the key and paste the picture here. And here you can crop it. What else you can do here? You can get the local values. You can click any point and get the electric potential value and the electric field stress components. You can calculate integral values. This is the integral value calculated for the entire cross-section. You can switch to the three-dimensional view, and again here I will hide the air block. I will switch off the cross-section. Here you can find the same instruments, the probing tool to measure the electric potential, electric field stress at different points, and you can find the integral tool. To calculate the integral, you should select the face, or you should select the body. These buttons are used to switch the presentation type. You can switch on multiple cross sections. You can switch on the vectors. You can switch on the scatter plot. And for the scatter plot again, I will switch to the electric field strength. So the red dots will indicate the places with high electric field stress. In this window, you can also build the contours by selecting the edges, make some plots. So this is the way how you can perform the three-dimensional analysis and calculate electric field stress distribution in the air gap of the spark plug.